All right, so what I have for you is an extra grade assignment. And the wonderful people at Flint Scientific, which is a company that we get a lot of our school chemicals and supplies from, have been doing a series of at-home labs and videotaping them, and they've been doing like live Zoom meetings and such. Since y'all are not available to go to their live Zoom meetings, I have taken what they've made pre-recorded and put it into and use their PowerPoint so that you are able to also experience these labs and see gas laws and how they apply to your everyday life. So let's get started in looking at this. So the first thing you're going to notice is that you do have a document both in OneNote and on Moodle that is going to be the actual assignment page that you fill out. There's going to be 3 different videos within this PowerPoint that you are going to watch. And you're going to try to answer the question that I have for each one of these videos. You notice that for each video there's an initial explanation and then a final explanation. Think of it as being like a your thoughts as to why or how things are happening. And then the final explanation should be the more sound science, the better explanation, the more scientific explanation for the phenomena that you see in the videos. All right, so the very first video, and hopefully what you should be doing is go ahead and print out that worksheet so that you have it next to you while you are watching this video. So if you haven't done that, take a second, pause this video, this screencast, print that out, and then press play again. Okay, so for this very first video, our friend here from Flint Scientific is going to do a demonstration with a soft drink can and using some different pressure. So what I'm going to do is I'm going to go ahead and play the video, let you watch what he does, and let's see if you can come up with an explanation as to why the soda can acts the way it does, both with unopened and when it is opened. So the first video is going to show him doing some demonstrations with pressure with an unopened soda can.
Okay, welcome to Flint at Home Science. You're in my kitchen. Let's do a little experiment here. Now we're going to do this and I'm going to ask you what the explanation is. So I have here just a simple soda can, or if you're in the Midwest, a pop can. It's got some soda in it, and I have some old college textbooks. Let's start to stack these on this. I'm going to move this out of the way. How many can it hold? And I'm just going to do this carefully to make sure that they don't fall off. I've got, what is that? We're up to 4, 5. These are pretty big books. A lot of knowledge in there. And this is holding them all. I'm not going to stack any more because I'm worried it might tip over. But now I want to do something else. Now let's put even more weight on this can. Can it hold me? Let's find out. Don't try this at home, by the way. Stand on this, and I'm going to support myself with this chair. Whoa! And then I'm even going to let go, and it supports all of my weight. Let me do that one more time. The cameraman is being patient. And again, it's supporting all of my weight, and I'm pretty heavy. So you can see there that this soda can, feat of engineering, can support a lot of weight. Okay, now let's try something else.
All right, so that was really pretty interesting. If you think about that soda can and how much weight and really pressure it can withstand. You know, soda cans are the metal, the aluminum that makes them up is fairly thin. So the question is, how is it that that soda can support so much weight or be under so much pressure?
Okay, welcome to Flynn at Home Science. You're in my...
All right, so for the next video, he's going to go ahead and open up that can of soft drink, pour all the soft drink out, and now let's see what's going to happen.
So, let's make another observation. What happens when I pour this out? Does this give you any clues as to why this can is able to support my weight? Now I'm going to pour all this out and then do another experiment. And hopefully I have enough room. Just right. Okay, now let's run this again after I've emptied out the contents of this can, the ginger ale. Let's see what happens when I start to stack the textbooks on this. Okay, so I'll start with the lighter one, this one, we're up to 3, up to 4, whoa, just reposition that, 5, 6, okay. Now let's see what happens when I try to put all of my weight on the empty soda can. I'm going to hold on to my chair here, safety first. And, oh, okay, that did not hold me. So, as you can see, this can could not support my weight and its volume has decreased. Let's talk about why that's the case.
All right, so let's talk about why is that the case. So, once again, your question is how come an unopened can of soda can withstand so much pressure versus an open can with all the drink poured out? So hopefully I'm going to give y'all a couple of seconds. If you need to, pause the video, write down what your initial thoughts are based on what your understanding is of Boyle's Law, Charles' Law, Gay-Lussac's Law, and KMT, Kinetic Molecular Theory, what's your understanding of pressure. A hint for all of these videos, you're going to see that your understanding of pressure is going to be really important in order for you to get a good explanation. All right, so I am going to try something out here. I'm going to try to use the pin feature, and let's see how that works out for me. All right, so you have this can, and originally, once again, here's something else I'm going to try out, and that is my drawing skills. So please be patient with me as I'm realizing this is going to take a whole lot more time. There we go. Let's try that all over again. Okay, so we have a can of soda. And when it is full of a solution of liquid and gas. The gas is under pressure in that can. That's how you are able to keep the gas in the liquid. The gas, of course, is CO2, and the liquid is some fabulously sugary, sweet drink. So if you have all of this CO2, and I'm thinking the best way to draw this is what? Remember CO2? We have a double bond. And let's see if I can change the color of the ink just to make it stand out a little bit more. All right, so there's our carbon, and here's an oxygen. Here's the other oxygen. And this is all in our liquid. So if we just say that our liquid is all the way at the top of the can, okay, and so the whole can is filled with liquid with all this carbon dioxide that's been dissolved in there. Now that gas inside the liquid, it has to be under pressure. So what we have here is that we have all of this carbon dioxide pushing up against the sides of our can, so that the pressure inside the can is greater than the pressure outside the can. So what happens, once again, if I go ahead and I go back to our green can, and this time if we open up the can, we pop the top of that can. As soon as you do that, and you experience this all the time, and you probably just haven't given it much thought, you immediately hear that pop noise, and if your hands are on the side of the can, you probably even feel that the can immediately, as soon as you pop that top, gets softer. And that is, we see a pressure release. And so now the pressure inside the can, so we can say pressure inside the can, is now going to be equal to the pressure outside of the can. And let's go back and try to change pen colors again. And here for this one, in which the unopened, and here I'll label it as well. Just to make it a little bit easier. Here in pressure, there we go, inside the can is greater than the pressure outside of the can. Okay, so that is why we see when he goes to step on the can, because we don't have this pressurized can anymore, that it immediately crushes once you put enough weight on it. So it held up the books just fine, but as soon as you go and put a person on there, a 200-pound person on there, we see that the can immediately crushes because pressure is now equal. We don't have this nice pressure from that carbon dioxide gas pushing up against the sides of the wall and helping the can to stay rigid, and like we see in the unopened can. All right, so moving on. All right, so here is the next video, the amazing Instapot. And for this one, your question that you are looking at is, how are you able to quickly hard-boil eggs in an Instapot versus trying to cook eggs on a stovetop? And really that would apply for any food that you put into an Instapot. It cooks really, really fast. And let's see if you can come up with a good reason why foods in an Instapot cook so quickly. So let's watch the video.
So I have here my Instapot. This was all the craze, if not this year, a couple years ago, or maybe a year ago. But let's explore the science of this Instapot. So I have here a cup of water, and I'm going to pour it in here. And, you know, I have a taste for some hard-boiled eggs, so I'm going to use my Instapot here. So, how many eggs am I feeling like? 2? Let's go with 4. Okay, now we're going to close this thing up. So now I've put the top on my Instapot, and I'm going to click manual. And this is going to take 5 minutes. Notice the little high pressure button is lit up there. Maybe you can't see that, but high pressure. That's going to be important. Cameraman's getting in closer. And we are going to hit, no, I think it started automatically. So we're good. Now, 5 minutes, we'll check back. Let's get our eggs out of our pressure cooker here, our Instapot. do that, notice the first thing I have to do. You hear that kind of hissing sound? Think about what that is. It's stopped. I'm going to open this up. And, oh, did you see all that kind of steam evolve? Think about that. And I'm going to give my eggs a little bit of time to cool. And now, I'm going to reach in and you can see that this is indeed cooked.
All right, so let's see here. All right, so within 5 minutes, he had hard-boiled eggs. And the reason why he was spinning it was to show you that the egg was cooked. A cooked egg actually spins faster around than a raw egg. It's another interesting phenomenon. If y'all ever want to try that out, hard boil an egg or two and spin it and compare that to an unboiled egg. And you'll see that they spin a lot differently. But anyway, let's talk about this Instapot and the fact that it could cook hard-boiled eggs in 5 minutes. So what is going on in this Instapot? Well, first of all, you notice that the high pressure light was on. So an Instapot is really a modern day version of a pressure cooker. That's all that it is. So what's happening here is that you are increasing the pressure inside the pot. That increase in pressure, all right, so I'm going to spare y'all a drawing of an Instapot. Maybe you were hoping I would give that to you, but no, sorry. So if we have an Instapot and we are going to maybe, let's try that again. All right, so if we increase the pressure in our Instapot, what's also going to be happening is that we're going to have an increase in temperature inside that Instapot. So this increase in temperature, what does that really mean? That means that the boiling point, because if you remember at the very beginning of the video, he put in 1 cup of water. So you will notice if you've ever done any kind of Instapot cooking, you always have to have a liquid in the pot. And it also has to be enough liquid in the pot. If you do not have enough liquid in the pot, it won't pressure cook properly. And in fact, I think it might give you like a warning light or give you a message letting you know that you need to add liquid to the pot. So you do need to have liquid in there, and that's really important because that increase in temperature inside that Instapot is going to increase the boiling point of that liquid water, which just means that that the objects inside there are going to cook much faster. Now let's see if y'all can also tell me which of the 3 laws has a the Instapot would be referring to. Would it be Boyle's law, Charles' law, or Gay-Lussac's law? Which one has a direct relationship between pressure and temperature? Hopefully you've answered Gay-Lussac. If you didn't, please go back to your notes and look at that and make sure you are spending some time with those 3 gentlemen and their gas laws and making sure that you understand the formulas and the relationships between which variables for which gas laws. All right, I think we can keep going. All right, here's another really neat one. So for this one, he has a jar of water and he has a valve. And what we are going to see is that he is going to go ahead and open that valve, have the cup underneath the spout, but nothing is going to come out of this jar. But when he opens the jar, we are going to see, and opens the valve on the spout, we are going to see that the water will start pouring out of the jar and into his cup. So the question is, why? Why does having the lid open or unopened on this jar make a difference in terms of the water coming out of the spout? So let's watch this video.
Okay, so I had a cocktail party New Year's Eve, and interestingly, the idea of phenomena as they pertain to gas laws came up, and the discussion centered around this thing that we had put out with a cocktail in it. Now I'm going to recreate the scene with water. So right now I have my top closed, I have water in here, I'm thirsty, I'm going to open this up to get a little drink. Nothing comes out. Nothing comes out. What am I going to do to parch my thirst? Quench my thirst, sorry, I said it wrong. So I'm going to close this now. So I asked my kids what they would do to get the water out. My son said you could tip it. So let's try his little philosophy there. And a little bit comes out, but still, Austin, it's not coming out. So we're at a loss here. We haven't fully understood the phenomenon here. So I'm going to reclose this. So now we had another idea. What if we open up the top and then try? So I'm going to open up the top. So now it is open, and let's see what happens here. The water is now free flowing. So let's talk about all the science behind this phenomenon.
All right, so let's see if I can get that. All right. So what our friend from Flint Scientific has done here is something very similar that you have probably done in any restaurant in which you have gotten a glass of drink with a straw in it. Anytime you put your finger on the top of that straw that's inside the drink and pull the straw out with your finger still on the top of it, you will notice that the drink stays in the straw. But as soon as you move your finger off of the top of that straw, the drink in the straw immediately comes out and is hopefully over your glass. And so that drink coming out of the straw is going back into your glass and not all over the table. And so it's the same idea here. And so if we draw this, and what I'm going to do just to make, well, nope, I'm not. Let's try that again. All right, so I'm going to try to do this right there. I'm going to do this as a straw rather than as the jar that the friend from Flint Scientific has going on. So if you have a drinking straw, yep, it's a pretty giant straw. And we have that in a glass. And we'll go ahead and get that straw all the way to the bottom. And so wherever our level of drink is in our glass is also going to be our level of drink in the straw. And so once again, if you just put your finger, oh heaven help us, I'm going to actually try to draw a finger now. So if you just put your finger over the top, and it's covering, if it actually did cover up the entire hole and then you picked it up, we're going to notice all that drink stays in there. Why? What is going on? The pressure inside the jar is less than the pressure outside the jar. So what's happened here is that you've kind of created, not kind of, you have created a vacuum. And so what happens, because you have created this vacuum, because you have a perfect seal over the lid, whether that's with your finger on top of a straw, or if that is your the lid on top of the jar, it's created this vacuum. And so once you've created a vacuum, there's less pressure. So when we look at that inside of our straw, the pressure here inside is less than the pressure outside. And so the water doesn't flow out. Okay, pressure always, things want to flow to where there's less pressure, less energy. Things always try to go from where there is more to where there is less. Things are not going to go from where there's less to where there's more. Okay, that's just one of the ways that the universe works. So as soon as you take that finger, once again, if we could show this as a animation, and you take your finger off the top of that straw, or you take that lid off the top of that jar, immediately the water is going to start flowing, whether that's out of a spout, out of the valve, or opening the valve and out of the spout, or out of the straw. Because once you remove that finger, now, once again, the pressure, so the pressure inside is going to equal the pressure outside of the jar or straw, whichever one. And this is with top off or finger, off the straw. Okay, so once you take the top off the jar or you take your finger off the straw, the pressure inside the straw or the jar is going to equal the pressure outside, and therefore the liquid can flow. All right, I think that is it. Yes. All right, so that is just some instances of everyday phenomena with pressure, with gases. And so there's so much about gases and pressure in your everyday life. Probably haven't given much thought to. Hopefully this will get you thinking a little bit more about how chemistry in your everyday life. And if you have any questions, please let me know. So don't forget to, if you need to, you can take a picture of your worksheet with your initial explanation and then with your final explanations that hopefully have a more science behind them. And don't forget to submit that to Moodle for your extra grade assignment.